the homework that should have been due Saturday, and I made it due Sunday. If for any reason you needed me to extend it a little past that, I will. That homework is just on the chapter 17, 16 and 17 things we did on Monday and Tuesday. Exams. The multiple choice part of it was easy. Just scan it in and the computer grades it. The other piece, the TAs were supposed to grade, and they haven't. And I simply haven't had time to sit down and grade it. I'm going to do those as soon as I can. I have interviews. I'm on a hiring committee, and I have interviews at 12 and 1, and somebody that's supposed to come in to help me with something at 2. But since I left my phone in the car anyway, I'm going to try and sneak out right after this class and get my phone and then come back and work on that grading. I know you guys want those exams back, and I'm a little upset that Brady and Thelina did not grade them. Thelina graded maybe 30% of one question and 2% of another question and then left the rest of it. So I'm a little upset about that, but I want to get that up. The other thing I need to get up this weekend is your review for the test that's coming up on next Wednesday, which is going to be on chapters 15, 16, and 17, which means it's a lot of icebox problems, regular icebox with acids and bases, and something that we're going to start on Monday, and that is iceboxes with precipitation reactions. So this test is pretty much iceboxes. But I want to do 15, 16, and 17 all together because when we start 18 next Tuesday, we're going to go in a completely different direction. Doesn't mean we're giving up on Ks, we're just giving up on iceboxes. So it's Friday, and I'm going to present you with not a fun lecture today. Thank you. I was going to say, please don't give me a duo push. I don't have my phone. But the it's basically the same stuff over and over again, but it's important stuff, and so I'm doing it over and over again on purpose. And it's all math. Everything today is just math. But there are only 56 slides in this because it's so heavily math and it's so annoying that I thought after less than an hour, maybe an hour of this lecture, you're probably going to be totally fried. So odds are you'll be able to get out early from this one, but this math is going to be tough. Okay, so we're still working on acids and bases because acids and bases are fun. What we want to talk about today is reactions between acids and bases. Now, our labs don't completely sync because we're doing 2 a day, 2 a week. So some of the things that you did in the afternoon lab on Wednesday may not have made a lot of sense, but it's not due till next Wednesday for a reason, because by the time we got through lecturing yesterday and we lecture today, you should be able to answer all the questions in that lab. They should make more sense. But when we put acids and bases together, they will undergo a double replacement reaction. A double replacement reaction is when 2 ionic compounds simply swap partners. In this case, I'm going to have an acid with an H+ and a base with an OH-. And remember, it's not just hydroxides that have OH-. Even the ammonia creates an OH- when it reacts with water. So I'm going to have the H of the acid and the OH of the base combining to make water. And then the anion of the acid and the cation of the base will create a salt. Now, the example I gave gives NaCl, what we think of as salt. But be aware that in chemistry, the term salt means any ionic compound. So we don't just mean HCl plus NaOH makes NaCl plus H2O. We mean that an acid plus a base makes some ionic compound. And this is a neutralization reaction. Because when we start, we've got an acid with a pH below 7, we've got a base with a pH above 7, and we want to end up somewhere in the neighborhood of 7 when we're done. In this case, we end up exactly at 7. But we're going to see today we don't always end up exactly at 7. But the definition of neutralization is simply going to be H plus equals OH minus. That is our neutralization. When the acid H plus exactly equals the base OH minus, it's neutral. Okay. So did someone mix your acid with a base because you're a bit salty today? I'm doing good today. There are days where that fits me. Okay, so HCl, NaOH makes NaCl plus water. That is a perfectly neutral solution. But not everything is a neutral solution. So here I have a weak acid, HF, with a strong base, NaOH. I make NaF. NaCl is soluble in water. NaF is soluble in water. Most of the salts that we create are going to at least be a little bit soluble in water, if not completely. My bad joke for the day, doctor, I think I'm a soluble compound. Well, we need to find you a solution. Like I said, bad joke for the day. I don't know, there may be another one in here too. The thing is that when NaCl dissociates, it is completely neutral. But when NaF dissociates, it is not neutral. Salt hydrolysis, what does an ionic compound do in water? And it turns out when the ions break apart, they do not necessarily need to give me a pH of 7. They could be acidic or basic. And whether they're acidic or basic depends on what the salt was made from. So neutral salts. Another ChemCat for today. I tried to come up with an acid spinoff, but I prefer to remain neutral. Neutral salts are made from strong acids and strong bases. These guys completely neutralize each other, and the salt that they create is completely neutral. So if my cation comes from a strong base, which means lithium, sodium, potassium, calcium, strontium, barium, if that's where my cation comes from, and my anion comes from a strong acid, like ClBrI or one of our strong polyatomics, then that is going to give me a perfectly neutral salt because the strength balances each other. When one is strong and the other one is strong, they're going to balance each other. And I end up neutral. So here are some examples of things that would create a neutral salt. Any of our group 1 or group 2 cations, our halogen anions, and some of the polyatomics. Now it does have a star there for H2SO4 because it is a polyprotic acid. The H2SO4 itself is strong, but the anion it creates, HSO4 minus, is also an acid. It's a weak acid. So they get a little star there. So that one doesn't work as well. But any combination of these guys, anything from the cation list with anything on the anion list is going to create a perfectly neutral salt. But if my cation comes from a weak base, like ammonia, and my anion comes from a strong acid, they're no longer balanced. The acid is stronger. And the result is going to be that the salt is acidic. So whichever one is strong is the one that determines whether the salt is acidic or basic. So a weak base and a strong acid will create an acid salt. So an example of an acid salt is ammonium chloride. Ammonium chloride is weak base, NH3, strong acid, HCl. So that is an acidic salt. Ammonium chloride, what do we use it for? It's smelling salts. That capsule they break open if you've passed out to try and wake you up. Because once you've got that guy, it does start breaking down to give you ammonia back. And so whenever you use smelling salts, you're just making somebody smell ammonia. All this stuff I tell you has nothing to do necessarily with what we're talking about, but you should know that there's chemistry out there. So this is the problem with an acidic solution. NH4 plus is the cation of a weak base. It is a weak acid. And it will react with water to give you ammonia back and an H3O plus. This is why it's acidic. There's already something in there from the strong acid, but now my weak base cation can react and give me H plus back. That's what's making it acidic, is that reaction of the weak acid NH4 plus to give me NH3 and H3O plus back. Basic salts are going to be exactly the opposite. We're going to have our cation from a strong base, which means lithium, sodium, potassium, rubidium, calcium, strontium, barium. And our anion is going to come from a weak acid. So NaF, sodium fluoride. HF is a weak acid. NaOH is a strong base. And now the situation is that F minus can react with water to give me HF back and an OH minus. So it is the reaction of the cation of the weak base, or the anion from the weak acid in water that creates whether or not it's an acid or a base salt. Because when you have something that's weak and it's a reversible reaction, you can get the reaction to go in reverse. And it can change the pH. So this is an example of a basic salt. So when both of them are strong, you know it's going to be neutral. When one is strong and one is weak, it's going to be whatever the strong one is. So in this case, the strong base makes it a basic salt. In the previous one, the strong acid made it an acidic salt. Another bad joke. Acetic acid and sodium hydroxide. Acetic acid is a weak acid. Sodium hydroxide is a strong base. So the result should be a basic salt. So combine them, it's a base. I think I put a bunch of those at the start here because I know how bad it's going to get as we go on. Okay. Now, what if they're both weak? What if both ions can hydrolyze? That means both of them come from a weak acid or a weak base, and they both can react with water. Well, then you don't know whether it's going to be acidic or basic unless you know the Ka and the Kb. So it would be whichever one was stronger. If the Ka is larger than the Kb, then it will be acidic. If the Kb is larger than the Ka, then it will be basic. And there's this weird guy. This is the salt made from acetic acid and ammonia. And I told you, there's only two things I know Ka is for, and that is because they're both exactly the same. They're ammonia and acetic acid. That salt, ammonium acetate, is actually neutral because the Kas of the acetic acid equal the Kbs of the ammonia. They're exactly the same. So that's a weird one where they're both weak, but it does happen to turn out to be neutral. So if I were to give you something that was made up of two weak things, I would also have to give you a chart of Kas and Kbs. And then you would simply take the larger of them, and that would be what determines whether it's acidic or basic. So ammonium nitrate, acidic, basic, or neutral? The ammonium ion, weak or strong? Do they come from a weak base or a strong base? Come on, somebody's got to know. It comes from a weak base. Xavier's not answering anymore. And NO3, strong or weak? Strong. It is strong. So I have a weak cation and a strong anion. Weak base, strong acid. So is this acidic, basic, or neutral? It's got to be acidic because this anion comes from a strong acid. So the answer is this is an acidic salt. Okay, acidic, basic, or neutral. Both of these come from NaOH, which is a strong base. But Cl minus, where does that come from? Strong or weak? That's one of our strong acids, right? So NaCl as a salt should be completely neutral because it's coming from a strong acid and a strong base. But if I make NaF, I know NaOH is a strong base, but is HF a strong acid? No. So that salt is going to be basic. It does help for the next test if you know what your strong acids and bases are. The bases are easy because, like I said, it's just group 1A and the bottom of group 2A and the hydroxides. The acids are a little harder because it's chlorine, bromine, iodine, but it's nitrate, NO3, it's sulfate, SO4, and it's 2 of the chlorates, ClO3 chlorate and ClO4 perchlorate. So they're a little harder to know because you kind of have to learn those. I'm not a firm believer, I'm not a believer at all in memorizing stuff you don't need to memorize. But this is easy. There aren't that many things to learn, so you can learn your strong acids without any difficulty. At least I think you should. Okay, what we're going to spend today on is titrations. I don't even know what lab you did for pH on Wednesday. Did you do a titration? Yeah, that's what I thought. So we're going to look at titrations now. We're going to spend the rest of the class looking at titrations. A titration is simply the process of adding a specific amount of an acid or base to a solution that you already have until you reach the point where they neutralize. And again, neutralize does not necessarily mean it's neutral. It does not necessarily mean it's at 7. The one that you did on Wednesday would not have been at 7. It would have been at like 8 point something. What's important at neutralization is that the number of moles of base added, the amount of OH minus, exactly equals the amount of H plus. The moles of these guys have to equal. That is neutralization. Whether your final product is at pH 7 or not, it is neutralized when the concentration of OH minus that you have exactly equals the amount of H plus. Okay, at that point, we're at something called the equivalence point. Equivalence point because OH minus equals H plus. The equivalence point is the point that we usually look for in a titration because it is the point at which they are equal. So if I have an unknown solution of a weak acid, for example, and I add sodium hydroxide to it, I know when they equal by finding that equivalence point. Okay, now, if I titrate a strong acid with a strong base, we're going to look in all these titrations we do today at 4 points. We're going to look at before we start the titration. We're going to look at the process between the start and the equivalence point. We're going to look at the equivalence point, and we're going to look at what happens after the equivalence point. Those are the 4 parts of the titration that you need to know how to calculate. Now, with a strong acid and a strong base, if I start with NaOH and HCl, I know that what I'm looking for is H plus OH minus goes to H2O, and that is a non-reversible reaction. Notice there's not a double arrow there. So because it's a non-reversible reaction, I don't have anything going back or forth and therefore my neutralization must occur at pH 7. So let's start with 25 milliliters of a 0.3 molar solution of perchloric acid. And I'm going to add 0.225 molar NaOH. Before sodium hydroxide is added, all I care about is that I have a 0.3 molar solution of HCl. Don't care how much I have of it. I can ignore for this first part the 25 milliliters. But I'm just going to do, before I start anything, where is the equivalence point? I need to find the equivalence point because I need to know exactly how much NaOH I'm going to add to get to that equivalence point. So if the problem says at the equivalence point, I need to know where that is. So I'm going to do a CV1 equals a CV2. So 25 milliliters of a 0.3. Why does that say 0.33? Okay. It says 0.33 all the way through, so I'm just going to make that 0.33. I don't want to have to do like I did yesterday and go in and change everything. So I'm just going to change that value. So at the equivalence point, 25 mils of 0.33 equals a certain volume of 0.225. That volume is 36.7 milliliters. Now notice, I didn't have to convert to liters here. Because I'm looking for milliliters, the molarities will cancel out. So if I start with milliliters, I'm perfectly okay leaving it that way, and it gives me my answer in milliliters. So 25 milliliters of that acid will need 36.7 milliliters of that base to neutralize it because the base has a lower molarity. So, okay, I got 0.3. Crap, I got this all mixed up. What was I doing? I got some of it in 3.0 and some of it in 3.0. Okay. If I have 0.3 molar HClO4, I have 0.3 molar H+. I don't care about the 25 milliliters. I'm just going to take the negative log of the 0.3, and my pH starts really low at 0.523. Before anything is started, all I have is acid. It's a strong acid, so I just have to say, what's the log of the concentration? Before the equivalence point, I need to know how much is neutralized and how much is not. So after the start, but before the equivalence point, the first thing I have to do is figure out how many moles of material I have. So number of moles of OH minus added is 25 milliliters, 0.025 liters, times 0.225 moles, or 0.00563 moles of OH added. Okay? How much H did I have? Well, initially, I had 0.025 times 0.300 moles of H+, or 0.00. Okay. I was doing this at home last night at 10 o'clock. I thought, yesterday was bad. It looks like today is no better. Okay. So I start with 0.0075 moles of acid. But every one of the OH minuses has neutralized an H+. So I have neutralized 0.00563 moles of the acid. When we're between the equivalence point, between the beginning and the equivalence point, you need to find how much you started with, how much you've added, and then how much would be left. So the amount of H+ I have left is 0.0075 minus 0.00563, or 0.00188 moles. So this is the standard we do for anything between the start and the equivalence point. Find out how many moles of material you started with, find out how many moles you've added, subtract the 2 to find out what you've got left of the original material. Everything else would have been neutralized. And now, this is the step, I've said this before, that students tend to forget. These have to be in molarities, and the volume is new. My new volume was 25 mils of HCl and 25 mils of base. So 0.05 liters, divide 0.00188 moles by 0.05 liters, and my new molarity is 0.0375. Take the pH of that, and my pH has jumped from 0.523 to 1.43. When we first start the titration, the changes in the pH are very small. But as we reach the equivalence point, we get a huge jump in the changes of pH. And then after the equivalence point, it will settle out again and have very small changes. So going from 0.523 to 1.43 is normal for this. Now at the equivalence point, the number of moles of base added equals the number of moles of acid, and this is strong acid and strong base. I don't have a choice. The pH must be 7 here. I don't even have to do, if I have strong acid and strong base, any kind of calculation. The pH has to be 7. After the equivalence point, I'm going to have excess sodium hydroxide. So I'm going to do the same thing I did before, and I'm going to figure out how many moles of H plus I had to start, 0.0075. Now I'm going to figure out how many moles of OH minus I added, and I've added 0.009. But now I have more OH minus than I have H plus, so I'm going to subtract the bigger one minus the smaller one. And it's going to tell me that I have 0.00150 moles of OH minus extra, left over after the neutralization. Again, there's a new volume. So I have to convert that to molarity. My new volume is 0.025 plus 0.4. So 0.00150 moles divided by 0.065 liters is 0.0231 molar. Now, this is an OH minus concentration because I'm after the equivalence point. So I'm going to do a POH. POH is 1.64, and look at how much my pH has jumped. My pH has now jumped all the way up to 12.36. Huge jump from 1.43 to 7 to 12.36. There's a huge jump there through the equivalence point. Now, strong acids and strong bases are fairly easy because it's just a matter of finding how much H plus you have or how much OH minus you have and taking the log of that, remembering to change your volumes. And the equivalence point must always be at 7. This is what it's going to look like. A, we have nothing but HCl. B, we calculate how much HCl is left. C has to be exactly 7. And D is how much excess NaOH I have. And so excess NaOH, I would simply do the pH from the POH from the excess OH minus and calculate the pH from that. So through all of these, you need to know how many moles of acid you're starting with, how many moles of base you've added, and then figure out what is going on. Have I neutralized part of the acid and have leftover acid, or have I neutralized all of the acid and have leftover base? So all of these calculations are going to involve finding what is the initial moles of material you're starting with, and how many moles of what we refer to as the titrant you've added. Now, strong acids and strong bases are pretty easy because we know C has to be 7. But we hardly ever do this with strong acids and strong bases. There's really no need to. The majority of things that we do with titrations is trying to determine the pH of an unknown solution that we know is either a weak acid or a weak base. So most of the titrations we do, one of them is strong and one of them is weak. Now, I just did strong acid and strong base, acid in your flask, base in the burette. I could do it the other way around and start with base and move to acid, but my steps would be exactly the same. What's the pH to start with? How much do I have after I've added some acid? Equivalence point is 7, and what happens if I'm after? So it's exactly the same as the previous example. I'm just going to switch the H's and the OH's, and my graph shows up backwards. I start at a high pH, and I end up low. But again, A would be the pOH of the base that I have, the strong base, and convert that to a pH. Then B is how much base is left after I've neutralized it. C is 7, and D is how much excess acid there is. So it's the same process, just flipping the H pluses and the OH minuses. But like I said, these are not things that we tend to do. We tend to do combinations of weak and strong. So calculations are going to be different here. Same 4 steps. Before we start, between the start and the equivalence point, and after the equivalence point. Same 4 positions we want to measure at, but our calculations are going to be different. So in this case, I'm going to take acetic acid, and I am going to titrate it with strong base sodium hydroxide. Because I have a strong base, my equivalence point is not going to be 7. My final salt is basic, so my equivalence point is going to be somewhere above 7. I don't know exactly where, but I know it has to be above 7. Now, exactly where it is above 7 depends on how strong or weak that weak acid is. How much above 7 it is will depend on the Ka of the acid. So you can see a strong acid starts out very, very low. Something with a Ka of 10 to the minus 4 starts out higher, but I still get a fairly good jump there. The top teal part after the equivalence point is exactly the same for all of them, because it's all just excess OH minus. But if my Ka is really low, 10 to the minus 8, I don't get a very good sharp curve. So I have equal amounts of the following weak acids titrated with 0.1 molar NaOH. So I'm comparing it to this chart. Which would have the lowest pH at the equivalence point of the titration, and which would have the highest pH? Well, according to this, the lowest pH is from the strongest of the acids. So looking at their pKa's, the strongest acid would have the lowest pKa. The weakest one would have the highest pKa. So the lowest equivalence point pH would be from the hypobromous acid, then the ammonium ion, and then phenol. So I'm simply looking at this chart and saying the stronger the acid, the lower the equivalence point pH is. The weaker the acid, the higher it is. So I'm looking at those pKa's, and a low pKa value means a strong acid. Stronger acid, I should say. Okay, so I'm now going to take 30 milliliters of a weak acid, 0.1 molar, with a Ka of 3.5 times 10 to the minus 4. It's not telling me exactly what this acid is. but it doesn't make any difference. The steps are going to be exactly the same. We're going to titrate it with 0.120 molar KOH. And it says assume that less than 5% of the acid ionizes in solution. If less than 5% of the acid ionizes in solution, that's our sign that we can drop the X in our ice boxes, because our check for whether or not we could drop the X in the ice boxes is it below 5%? So that's what they're telling me in that sentence. Assume that less than 5% of the acid ionizes. They're telling me I can drop the X in an ice box. So the first thing I'm going to do is find my equivalence point. 0.1 molar times 30 milliliters is equal to 0.12 molar times some new volume. Now in this case, I did convert the milliliters to liters. I didn't in the previous one. It doesn't make any difference which way you do it. You don't have to convert, but you can. So my volume is 0.025 liters or 25 milliliters. The molarity of the base is a little bit higher than the molarity of the acid, which means I'm going to need a little bit less volume of it to get to neutralization. So at the start of the reaction, before any KOH is added, I have a weak acid with a Ka. I need to do an icebox. So HA is 0.1, H plus and A minus are 0. So 0.1 minus X, X and X. And I did drop the X. I checked, it wasn't really good, but the problem did tell me that I can drop the X. So Ka is X squared over the initial concentration. K is 3.5 times 10 to the minus 4 equals X squared over 0.1. So X squared is equal to 3.5 times 10 to the minus 5. X is equal to 5.92 times 10 to the minus 3, and my pH is 2.23. Not 0.5 like the strong acid was, but still an acidic solution. So before anything starts, we want to do an icebox using the concentration of the acid that we're given and drop the X. Like I said, I dropped the X. I checked, and it says I shouldn't have dropped the X, but the problem said drop the X. So that is 0.1. What is the pH before you start the titration? Okay, now I went ahead and calculated a pKa here because I'm going to use the pKa in the next step. So the pKa here is 3.46. After 15 milliliters of KOH is added, I have to know how much H plus I started with, I need to know how much OH minus I added, and I need to know what's left. So I started with 0.003 moles of HA, 0.1 molar times 30 milliliters. I've now added 0.12 times 0.015 liters, 0.00180 moles of KOH, or OH minus. I'm going to do the same thing I did with the strong acid and the strong base, and I'm going to subtract those two to see how much HA I have. So I have 0.00300 minus 0.00180, 0.00120 moles of HA left. The difference in this versus the strong acid and the strong base is we're not necessarily going to say I react all the HA, how much HA do I have left, and that's all I'm worried about. Here, I'm producing A minus, and this is a reversible reaction, so the A minus becomes important. But the A minus concentration is going to equal the OH minus concentration. We're going to allow the OH minus to completely react and completely convert to A minus. So the 0.00180 moles of OH minus I added is now 0.00180 moles of A minus. So now I have a concentration of the base A minus and a concentration of the acid HA. I could do an icebox. But if I have a concentration of a base and a concentration of acid, I can use Henderson-Hasselbalch. And with Henderson-Hasselbalch, volumes cancel, so it tells me I don't even have to convert with that new volume. I can use the moles straight. So the pH equals the pKa plus the log of the base over the acid. The base is the 0.00180 of the OH minus I added. The acid is the 0.00120 of the HA I have left. So 3.46 plus the log of 0.0018 over 0.0012, which is 0.176, and my pH is 3.64. Between the start and the equivalence point of a titration with a weak acid or a weak base that is a reversible reaction, we just have to find the moles of what we started with and the moles of the conjugate and do a Henderson-Hasselbalch. No icebox needed here, which is nice. So my pH, after adding 15 milliliters of KOH, has gone from 2.23 up to 3.64. As I said, it's kind of a slow increase to start. So what happens at the equivalence point? This is where these problems become difficult. Because at the equivalence point, we have no OH minus, we have no HA, all we have is A minus. All of the OH has reacted with all of the HA to produce water and A minus. At the equivalence point, all I have is A minus. So if I allow all the OH to react with the HA, I'm going to end up with all A minus. So the moles of A minus that I have will equal the amount of HA that I started with because there is now no HA left. So I started with 0.00300 moles of HA. That is now what I have for A minus. But now A minus is a conjugate that reacts with water. This is going to be a basic solution because A minus reacts with water. It gives me HA back and OH minus. I'm going to need to do an icebox here based on the concentration of A minus. But that's the conjugate base. So I can't use the Ka. I have to know a Kb for this. But Ka times Kb is Kw, which is 1 times 10 to the minus 14. So the Kb is 1.0 times 10 to the minus 14 divided by 3.5 times 10 to the minus 4, which is 2.9 times 10 to the minus 11. We know that if we have a weak acid, the base should be even weaker. And it is. That Kb is really low. So now, what I need to do is use that Kb. I do at this point have to use a new volume because I'm going to make an icebox with A minus. So I'm going to take the original moles of HA, make them the moles of A minus, divide it by the new volume, and get a new icebox. So at the equivalence point, all the acid has been converted to the base. I need to do an ice table of the conjugate base. I do have to convert to molarity. If my new volume is 0.05 liters, then my new molarity of the A minus is 0.060 mole. It's less than the 0.1 that we started with because the volume is now bigger. So 0.06 minus x, 0, 0. I'm going to drop that x. I know that k is super, super small. There's no problem dropping that x. So 2.9 times 10 to the minus 11 equals x squared divided by 0.060. 0.060 times 2.9 times 10 to the minus 11 is x squared, which is 1.7 times 10 to the minus 12. X is 1.3 times 10 to the minus 6. But this is not an H plus concentration. This is an OH minus concentration. So from that, I'm going to get a POH. And my POH is 5.88. Subtract that from 14, and my pH is 8.12. So we can see for this weak acid, the salt we create is basic. The equivalence point is greater than 7. Now, after the equivalence point, It's exactly the same as anything else. How much OH minus have I added? Neutralize all the HA, get extra OH minus. So after the equivalence point, figure out how many moles of OH minus you've added, subtract off the amount of HA you started with, divide it by the new volume, and get a molarity for the base. Take the log of that, gives me a POH, subtract that, and I can see, again, I jumped from 8 to 12. So the steps in using a weak acid and titrating it with a weak base are step 1, simply do an icebox for the weak acid. I dropped the x because the problem said I could. Ka is equal to x squared over the initial concentration. I solved for x and took a pH of it. That is always the first step. Before you add any of the titrant, you just do an icebox for whatever it is you have. And we've done tons of these iceboxes, so this should not be that difficult. Not fun, but it shouldn't be that difficult. Okay, between the equivalence point and the start, I need to know how many moles of KOH I added and how many moles of HA I started with. I'm going to convert all of that OH minus to A minus, and then I'm going to subtract that amount from the original HA and get how much HA is left. Now I have a quantity of A minus, I have a quantity of HA, and I use Henderson-Hasselbalch. Okay, so in step B, know how much you started with and do it in moles. Know how much you added, subtract the two. And I have to do this in moles because I can't subtract a molarity. So moles of HA to start, moles of OH minus added. The moles of OH minus become the moles of A minus, and I subtract that from HA to get how much HA is left. Then do Henderson-Hasselbalch. Okay, this is the one that confuses most of the students, is at the equivalence point, there is nothing left except A minus. The amount of A minus I have is equal to the amount of OH minus I've added, because all of the OH minus has worked to remove all the HA. If I have 0.003 moles of HA to start, I've added 0.003 moles of OH minus, and I have 0.003 moles of A minus created. So the amount of A minus I have is exactly equal to the amount of HA I started with. But then I allow A minus to react and produce OH minus. I need a K for the conjugate for that. So to find the K for the conjugate, I simply divide 1 times 10 to the minus 14 by my Ka, get a new Kb, and now I do a new icebox with the A minus. But this time it's going to give me a POH. And then I subtract that from 14 to get the pH at the equivalence point. And after the equivalence point, I find out how much OH minus I've added. I subtract the amount of HA I had to start, convert to a molarity, and get a POH and convert to pH. Those 4 steps are always going to be what we do when we have a weak acid with a strong base or a weak base with a strong acid. Do an icebox of the original, do the Henderson-Hasselbalch in between, do an icebox of the conjugate for the weak acid with the strong base, the pH will be greater than 7, and above that, excess NaOH. Now, if I do it the other way, a weak base with a strong acid, I'm going to do the same 4 steps. I'm just going to do it with the base. So I'll be given a Kb. And when I'm done, my equivalence point should be acidic. It should be less than 7. So I want to do an icebox of the weak base. Again, they're telling me assume less than 5% ionizes, so I can drop any x. So at this point, my Kb would equal x squared over 0.200, and that would give me x would be equal to OH minus, and that would give me a POH, and I subtract it from 14. So same step, I'm just doing it for the weak base instead of a weak acid. At this point, I'm halfway to the equivalence point, which means I'm going to use the Henderson-Hasselbalch. How much base did I start with? How much acid did I add? The amount of acid I added is now all conjugate acid of the base. Figure out how much base I have left by subtracting those two and using the Henderson-Hasselbalch. Now, Henderson-Hasselbalch is pH equals pKa plus the log of the base over the acid. I have a Kb here, which means that to do Henderson-Hasselbalch, I must convert my Kb to a Ka. Because Henderson-Hasselbalch only uses Ka. At the equivalence point, I would do the icebox of the conjugate acid. I should already have a Ka. I just need to make sure I use the new volume. The number of moles of the conjugate acid is the same as the number of moles of base I added. Use the new volume to find a molarity and do an icebox for the conjugate acid. And then after the equivalence point, I just have excess of that strong acid. So exact same process, just backwards. An icebox of my original base, my Henderson-Hasselbalch of a mixture of base and acid, the icebox of the conjugate, and excess HCl. And notice that C is below 7 now. Okay, well, in this one it says half equivalence point. Why? What's important about the half equivalence point? I could do anything between the start and the equivalence point. Why specifically did that problem ask for the half equivalence point? Okay. At the start, I have only HA. At neutralization, I have only A minus. At the half equivalence point, I've reacted half of my HA into A minus. At the half equivalence point, halfway between the start and the equivalence point, I have equal amounts of HA and A minus. I've reacted half of the HA, so I now have 1/2 of the HA and 1/2 of the HA is now A minus. So the amounts of HA and A minus are equal. And it doesn't make any difference whether I'm doing this one with a weak acid and a strong base, or this one with a weak base and a strong acid. At the half equivalence point, whichever one you're doing, if HA equals A minus, then I have the log of 1, and the log of 1 is 0, so my pH equals my pKa. If I have an unknown acid or base, using the equivalence point, finding the equivalence point, then using half that volume to find half the equivalence point allows you to calculate Ka. This is what you were doing on Wednesday, wasn't it? Yeah. Like I said, I'm sorry you did it before the lectures, but there's no easy way to spread them out. So the half equivalence point is important to us because it gives us a way to find a Ka if we do a titration. Now, half equivalence point means half the volume, not half the pH. So if the pH here is 7, well, 6 point something, it's actually not 7. I don't want a pH of 3.5. I want a volume that's half of the equivalence point volume. So I'll get back to the other slides. So if I'm plotting this, if I'm looking for the equivalence point by graphing, I end up with something like this. And the equivalence point will be the center of that sharp jump. So they gave me a set of data here. This is obviously a weak base with a strong acid. My equivalence point is below 7, and I started up at 11 point something. And it tells me this is where my equivalence point is, below 7. So my equivalence point was at 25 milliliters with 5.28. My half equivalence point would be half of that. My half equivalence point is at 12.5 milliliters. I don't actually have that data here, but it would be someplace between 9.1 and 9.4. So when you do have equivalence point, we're looking for half the volume, not half the pH. Now we're almost done. I told you we'd get out early today because I'm pretty sure you guys need to go home and think about these steps for equivalence points without me dumping more stuff in your brain. So I just want to do a couple more slides. Polyprotic acids. This is a thing where I have H2A goes to HA minus and A minus 2. I'm creating water. I'm creating H plus at every one of these steps. Each one of these steps, we saw from a previous lecture, has its own Ka. Therefore, each one of these steps has its own titration. So the book gives an example of malonic acid. Malonic acid is a diprotic acid. Those H's at the end both come off. And the book gives me these two reactions and then fails to give me a graph. I had to go look for a graph. So I have a Ka1 of 1.4 times 10 to the minus 2, and I have a Ka2 of 2.0 times 10 to the minus 6. I get two curves here. I get a half equivalence point associated with the pH of the pKa at 2.85, and I have a second peak that gives me a half equivalence point of 2.0. So the blue spots are the equivalence points. The blue spots are not the half equivalence points. The half equivalence points would be, if this is about 25 milliliters at about 12.5, there's my half equivalence point. This half equivalence point is, that's at about 50, so at about 25, my half equivalence point is about here. Okay, so whenever I have a polyprotic acid, there are two steps. Now, doing a polyprotic acid with an ice box on a test isn't difficult because you just do the first ice box and find the H plus from that, and then your conjugates, what would be, on the previous slide, A minus and HA minus and A minus 2. Oops, I think I'm too far along. So I would do an ice box for the first step, but for the second step, to find A minus 2, I thought I had a slide that said A minus 2, maybe not. A minus 2 would just be equal to the Ka2. That's not too difficult. Doing that for a polyprotic, doing the ice box on the first H plus loss, and then setting the first conjugate, that HC3H2OH minus, equal to the H plus. And then the second conjugate, the minus 2, just becomes equal to the Ka. So finding all of those things in an ice box for concentrations is one thing. Dealing with one of these polyprotic titration curves, I'm not going to give you on a test. Okay? So this is the end of acids and bases. It is not the end of chapter 17. We will on Monday talk about precipitation reactions and K values associated with precipitation reactions. They're even easier than K equals x squared over the initial concentration because there is no denominator in those guys. But we still will be doing Ks on Monday. So review for the test. I will get up as soon as I can, but it's going to be a heck of a lot of icebox type problems. If you have 5 long answer problems, I promise I will not give you more than 2 that are ice boxes, and one should be fairly easy compared to the other. One should be an acid base where you just do x squared over the concentration. The other one might be a polyprotic type thing. I don't know, haven't written it yet. I have to take a look. But like I said, I've given you a lot of stuff on how to do titration curves. You need to go home, you need to let this soak in and think about it. Xavier's going, yes. So I'm not going to move on from here. I'm going to leave this here and start a new topic on Monday. Okay? Have a good Friday. Have a good weekend. It's supposed to be cloudy this weekend, but they say the rain's going to hold off till Monday.